Okay, so we looked at polar coordinates where now our unit vector is rotating with this angle theta. And by knowing what is theta and the distance from that reference point, you can define the position of this object or the particle that is being tracked. And so you have r changing as a function of time and theta changing as a function of time. And with this, you're able to model the motion of different kinds of measurement systems, whether it's video tracking or radar tracking or any case where it's helpful to or possible to know the radial distance and the angle at any instant of time. Okay. Let's now consider the special case where the radial distance remains fixed. So you have now the same reference and you have a theta that can change. So this here is your theta of t. And what I'm now saying is that this r of t is now changed to some fixed constant value r. Okay, so how is the motion going to be? I think it's rather straightforward. It's just a circular motion. And so the particle's motion is now constrained to move in this circular path because the distance from that reference point is fixed to be capital R. Let's say that we still want to study this using polar coordinates, which means we have R being R of t e r hat, wherein this has now become a constant R, right? That's the change from the polar coordinate system. So if I were to write R is equal to capital R E R hat, now V, according to the polar coordinates, is R dot E R hat plus R theta dot E theta hat, right? What is E R hat? It was radially outwards. Always remember that. It's radially outwards. And what is E theta hat? It is in the direction of increasing theta. This here is E R hat. This here is E theta hat. And what happens now is that since R dot is a differentiation of a constant, this goes to zero. And we're left with R theta, which in this case becomes capital R for a constant, theta dot. So that means the velocity is R theta dot in this direction. And what about the acceleration? According to the polar coordinates, you had R double dot minus R theta dot squared E R hat plus 2 R dot theta dot plus R theta double dot E theta hat, right? Again, this goes to zero because R is a constant. R dot also goes to zero because R is a constant. And so now you have that the acceleration is minus R, and in this case, this R here, I'm going to rewrite it as capital R to represent the fact that it's a constant, and the same over here, capital R for the radius. Um, so you have minus R theta dot squared ER hat, which means it's in the opposite direction of ER hat. It is going inward. This is probably something you've already learned as the centripetal acceleration or the acceleration that's pointing towards the center, right? So this here is your centripetal acceleration. And this here is along E theta hat. You have R theta double dot. That is your tangential acceleration. So if I were to write this as just a magnitude, then a magnitude, or also called the normal acceleration for centripetal acceleration, would be AN, which is inward, is the normal or centripetal acceleration's magnitude is r theta dot squared, or you can write it as r omega squared. And at, or the tangential acceleration, is equal to r theta double dot, or this is r alpha. So all of this stuff here related to the acceleration, and this here related to the velocity. So if I were to now write down the magnitude of velocity, or the speed, this is going to be equal to, I'm defining it as v, not the vector, the scalar v is equal to r theta dot, or r omega. And if you now want to relate that with the normal acceleration, then we have that this here is r omega squared, which means I could write that an, which is basically r omega squared, is the same as writing v square over r. Right, that will be r square omega square over r. That makes it r omega squared. And so we now have that v is equal to r omega, an is equal to v square by r, at is equal to r alpha. Is there another relation that you can obtain from this here? You could also multiply v with omega, right? This will become r omega squared. So I could also write this as v omega. So these are some relations that you can make use of. I guess to make it complete, I should also write that this is equal to r omega squared. So these are the relations for circular motion in terms of just the magnitude. You should remember that these values are, in case of normal acceleration, it's inward, which is why there's a negative sign over here. In case of tangential acceleration, it's along this direction, that's increasing theta. And the velocity is also in the same direction. Okay, so all of this that we've just been discussing is the special case of circular motion where your radial distance is fixed. Okay, so I think this is familiar to you guys, but let's do a few problems. First, we have the case of a bicycle wheel that is being serviced. So I'll write down the question. So this here's a question. You have a bicycle wheel rotating at 45 RPM, and we're trying to find the speed and magnitude of acceleration of a point on its outer rim. Okay, so there's just an application of what we've been looking at. Try it yourself, rather straightforward. You have that there is a bicycle wheel. I'm drawing it as this dotted circle for the circumference or the outer rim. Um, it has a diameter of 0.6 meters, so I would draw a radius of 0.3 meters, and it's rotating at given 45 RPM. If only this much is given, you can assume that it is rotating at a constant speed of 45 RPM. So now you'll find the speed and the magnitude of acceleration. In this case, v is equal to r omega, right? So r is 0.3. Omega is not 45. It is 45 rotations per minute. You have to convert that into radians per second. 45 rotations means 45 times 2 pi radians. That would be in 60 seconds. So we have to divide by 60 to convert it to radians per second. If you were to now plug this into your calculator, you will get 1.413 meters per second, and that is your speed. Um, as for the acceleration, there are two components. There is the normal component, which you can write it as v square by r or r omega square if you do either of them. So in this case, I'm doing v square by r, and I will get 6.65 meters per second square. Tangential acceleration is r alpha. In this case, it's zero because it's given that the wheel is rotating at a certain speed. It's not telling you how that's changing, so you can assume that it's constant. And this means that the net magnitude of acceleration is 6.65. If instead you had some magnitude here as something like, let's say, 2, then you would have to have a is equal to root over 6.65 whole square plus 2 squared whole under root. Okay, keep that in mind. Um, with that, let's do a more interesting question. So you have, I'm actually going to pause and then create the question myself. So this here is the question. You have this horizontal path, which means that we're viewing this from the top view. There's a particle that's starting at position A at rest, and its speed is increasing constantly at 2g along the horizontal path. What is the meaning of 2g? It is 2 times gravitational acceleration in meters per second square. You can use 9.81, or in this question, I think I'm going to use 10 meters per second square as g, just for the sake of calculation and writing down the numbers. And what the question says is that you have to determine the magnitude of velocity, as essentially the speed, and the total acceleration at point B just before entering the circle. So that's where it's still executing rectilinear motion. And then at point B just after entering the circle. So that means it's now executing circular motion, but its speed would be the same as it was at this position just before. And at point C, where it has completed 90 degrees of this rotation. Okay, so pause the video and try it yourself. For the first part, that is point B, just before, I'm gonna define this as B minus to represent that it is just before entering the circle. And that is this yellow highlighted point over here. So this is now essentially rectilinear motion, which we looked at a while ago. You have your initial speed as u naught is equal to 0. You have acceleration as 2g, which I'm going to write as 20 meters per second square. The distance is given to you as 3 meters, and we're interested in what is ub minus. So what formula would you use here? Because it's constant acceleration, you have access to those familiar formulae, which is v is equal to u plus at, s is equal to ut plus half at square. In this case, we are interested in ub minus square minus u naught square is equal to 2as. This here going to 0, and then substituting the values of a and s, you will get ub minus is equal to 10.95 meters per second. What is the acceleration at this position? Is the same as what is the rate of change of speed. So it would be the same 20 meters per second square because it's just executing rectilinear motion, right? Straight line motion. But what about point B just after entering the circle? So this I'm going to call B plus. In this case, the speed is the same, so that's given essentially, because that's the meaning of just before and just after. It should be 10.95 meters per second. Since it says that the speed is increasing constantly, what this means is that the tangential component is still the same, 2g. That is, I'm going to call this B plus. Tangential is 20 meters per second square by definition. And what about the normal component? This would then be, you could use v squared by r omega square. In this case, v squared by r seems most appropriate because we have the speed given to you and you have the radius as 3.5. So v squared by r gets you 10.95 squared divided by 3.5, which if you plug into your calculator, you should get 34.26 meters per second square. So how do you answer the question of the total acceleration? Which one do you pick? Do you pick this or this? Well, neither, because these are components of the total acceleration. So you have to account for the fact that they are, well, one is going to be aligned tangentially, and then one is going to be aligned towards the center, right? So this here is tangential, and this here is towards the center, and they are perpendicular to each other, which means that the net acceleration A is root over 20 squared plus 34.26 squared, which gives you 39.67 meters per second squared. So even though its speed is increasing constantly, the moment it has entered this circular motion, because you now have this normal component of acceleration, it is then creating this jump in the acceleration. Previously it was 20 meter per second square, now it's almost double. Okay, simply because it is going from a straight line path to now having to rotate about this point, so executing circular motion. The next part of the question asks for point C, which is after executing circular motion for this 90 degrees, what is the distance that is covered? So S from B to C is equal to, is essentially the arc length, right? So note here that the speed is still increasing constantly, which means whatever speed here, now as it goes through this distance, it is still continuing to increase at 2g. So here the distance is arc length, which is 3.5 times the angle in radians, that is pi by 2. Why is that? If this here was a circle and you had an angle of theta, then this arc length would be r theta for a circle of radius r. In this case, the theta is 90 degrees, which is pi by 2 radians, and the radius is 3.5, which is why you get this as a distance to be covered, which is, well, I guess I'm going to just leave it as this in meters. What is the speed at at position C? That is unknown. The speed at position B is given to us 10.95, and the acceleration is still the same as 20 meters per second square. So in this realm, we're still dealing with the same equations that we had for rectilinear motion, but because it speaks about speed increasing constantly, uh, it's being applied in the tangential sense. So this here's AB tangential. We can now apply v square minus u square is equal to as again. So uc square minus ub square is equal to 2ab tangential times s from b to c. And if you were to plug in the numbers, you will get uc is equal to 18.43 meters per second. So speed has increased from 10.95 to 18.43 as it executes this 90-degree rotation, since the speed is still increasing constantly at 20 meters per second square. So at this point, you have the tangential acceleration that's still given to you, and the normal acceleration that is, well, I think I made a mistake in writing down the index. It should be C everywhere. Yeah. So it was the tangential acceleration that was at position C. Now the normal acceleration position C is, you can use v squared by r omega. You can use either of these. In this case, you have the v, the speed, and the radius, so you can just use uc squared by r, giving you 18.43 squared divided by 3.5, giving you 97.1 meters per second square. Well, that's not the final answer. The speed which was of interest is here. The net acceleration is now again 20 squared plus 97.1 squared, which is going to give you 99.14 meters per second squared. So from this point here, where the acceleration was 20 meters per second square, as it's gotten to this point, the acceleration has increased by a factor of 5, pretty much. Um, that's simply because of the speed increasing as it's executing the circular motion, and you have to account for how normal acceleration is being set up in addition to the tangential component. Okay. Um, so what this example really tells us is that as this body is starting, or particle or rigid body or whatever it is, as it's executing circular motion, the speed is defined based on the tangential acceleration, but the fact that it's executing circular motion, it sets up a normal acceleration so that it can change direction. So essentially, the tangential acceleration is responsible for changing the speed, and the normal acceleration is responsible for the rotation. Okay, so if we were to now look at, let's say, a general motion of some part that maybe looks like this, and the particle is going from the top left in this way. So here, there's the direction of motion. And let's first look at what the velocity is going to look like at every instance along the path. The instantaneous velocity will be tangential. So this here is tangential. Okay. So there's a direction related discussion. And what about the magnitude? That magnitude might be changing. The magnitude of velocity or the speed will be changing based on the tangential acceleration. If it is aligned along the velocity vector, then the magnitude of velocity or the speed would increase. If instead it was aligned in the opposite direction, then the magnitude of this vector would decrease as it's going forward. Okay, so the tangential component is always going to be tangential to the path, either with or against the direction of velocity, while the normal component is what is responsible for the rotation, and that will always be perpendicular to the velocity, and it will be pointed in the direction towards the center of rotation. What does that mean? So at the moment, I'm just drawing perpendiculars. So your normal component is going to be perpendicular to the velocity. And essentially, you can consider at every instant that there is a circle here that represents just that section of the motion. Okay, so this here's me trying to draw a circle for this part of the trajectory. Here's me trying to draw it for this other region. Okay, so as it moves along this here is the circle that represents the rotation that's happening over there. Over here, of course, the circle is going to be much larger. Let me see if that comes out as a circle. No, it didn't. It would be a much larger circle, perhaps like this. And in this section, where it's essentially a straight line, that circle would have a radius of infinity, right? So it's a circle that, when you look at it close enough, it looks like it is a straight line, but in fact, the radius is infinity. And you don't know if it's on the right side or the left side. But the circle over here now has changed the direction of that normal acceleration from initially being to the left of this trajectory to now being on the right. Okay, so you can consider that the path of any object as it moves along some trajectory is constituted by multiple circles that are connected together. Okay, so this minuscule arc over here represents how the rotation is happening at this instant of this trajectory, and over here, the arc over here, which is related to this circle, represents how the rotation is happening and so on. So what really is the radius of this circle? Um, if you have a way of obtaining the net acceleration, then that acceleration is composed of the tangential component and the normal component. And if you know the velocity, then the normal component of acceleration is going to be v squared by r, right? So an being equal to v squared by r gives you the normal component, wherein this here is the radius of curvature. Okay, so at that instant, whatever is the normal component of acceleration, it gives you what is the radius of curvature, which is the circle whose arc subtends that particular section of the trajectory. There's no problem to make this rather clear. So in some coordinate system, we have that a particle is moving according to x is equal to 2t squared plus 3t minus 1, and y is moving according to 5t minus 2. The question asks you to find the radius of curvature at 1 second. Okay, so what coordinate system are we using here? This is a rectangular coordinate system because you have r being defined as 2t squared plus 3t minus 1 along the I hat direction, and y being defined as 5t minus 2, which is along j hat direction. So it is not immediately clear what is tangential, what is normal, but you can write that the velocity would be, in this case, a differentiation of the component along I, which is going to give you 4t plus 3 along I hat plus 5 along j hat. And the acceleration would be 4 I hat plus 0 j hat. So this is dependent on the rectangular coordinate system, but we can now break down the acceleration into a component that is along the direction of velocity and a component that is perpendicular to the direction of velocity. And that would give you the tangential and normal components. Okay, that should be your strategy. Go ahead and try for yourself. Essentially at t is equal to 1 second, the velocity is going to be equal to 7 I hat plus 5 j hat, and the acceleration is still just 4 I hat. Okay, so we have that there is velocity that has a magnitude of 7 along I hat and 5 along j hat. So you have some angle here for the velocity vector with respect to the x-axis. What is the magnitude of velocity? This would be root over 5 square plus 7 square, which is 8.6 meters per second. And what about the acceleration? It is just 4 I hat. So we have to draw that overlapping over here. This here is your acceleration at 4 I hat. Okay, I just put the unit so it's clear that this here is velocity and this here is the acceleration. and the magnitude of velocity is this much. Okay, what are we trying to do? What is the whole point of this? We want to understand how much of the acceleration is along the velocity. So how much of this component along velocity. So I want to know what is essentially this 4 cos theta. So AT would be equal to 4 cos theta, and A normal would be equal to 4 sine theta, right? So 4 cos theta plus 4 sine theta gives you your net acceleration. And this A normal is equal to V square by R, where we have already V is 8.6 square divided by R. We don't know theta yet, but that's an easy fix. So you can do theta is equal to tan inverse of 5 over 7 to obtain 35.5, or you could directly have that sine theta is equal to, so if you look at this triangle, right triangle, this would be 5 over 8.6 would be your sine theta. So in kind of writing it in rough as I'm solving this problem in real time, um, but this is how you'd approach it. So you always want to write down what do you know, and then what do you not know, and then you try to reduce how many other things you don't know. So in this case, we now have that 4 times 5 over 8.6 is equal to 8.6 square over r, giving you, if you were to now solve this, you get r is equal to 32 meters. So that means that as it's executing its motion, in a motion that is defined in this way, we have found the velocity, we have found the acceleration, we looked at the component of acceleration along the direction of velocity, that is a tangential component. We don't really care about that because it's asking for radius of curvature. So now we found the component of acceleration that is perpendicular to the velocity, that is this here, which is going to be equal to v squared by r. And from that, we found r as a radius of curvature, which means as it's executing this motion, that'd be a circle whose radius is 32 meters, which represents the radius of curvature at this instance. Let's do another problem. So this here's the question. The total acceleration of a train is given. So how do you find this? There are many ways that this can be measured. There are inertial measurement units that can provide you with the acceleration at any instance of time. Those of you who are into motor sports, you might have seen a circle in which there is a point that moves somewhere within the circle, representing how many g's of acceleration or uh, braking or turning. So you can represent that within a circle. So there's also some representation of the acceleration of a vehicle as it's executing accelerations and turns and so on. But essentially, the total acceleration can be measured. There's going to be including the tangential and normal components. Given that the train speed is known to you and it's known that the speed is increasing at this rate, then the question asks you what is the radius of curvature. Okay, I hope this is understandable. Of course, you can always email me if there's something I said that's confusing, or you can schedule office hours. Um, yeah, try to solve this yourself. Okay, so again, let's write down what we have. Essentially, since the speed is increasing at 3 meters per second, that means that the tangential acceleration is 3 meters per second square. We have that the net acceleration, that is A, is equal to, it's given 5 meters per second square. And we know that this here is equal to root over an squared plus at squared, which then gives us that this here is And if you were to solve for this, then you get an is equal to 4 meters per second square. Now we know that an is equal to v square over r, which is equal to 20 square over r, which we just found is equal to 4, giving us the radius of 100 meters. So essentially, at this instance, as the train is moving along the circular, according along the radius of curvature, along the railroad, its speed is increasing at 3 meters per second square, but because it is having some curvature in that region of the railroad, the component that is normal acceleration, we found that first, and then we equated that to v squared by r to then find out what is the radius of curvature. Okay, I hope this makes sense.